Welcome to this deep dive into the really fascinating world of number sequences.
Glad to be here.
Today we're venturing into the online encyclopedia of integer sequences, the OEIS, as most people call it.
An indispensable tool.
And we're focusing specifically on one entry, ALE0190. If you're studying number theory, this one's a really neat example of some core ideas.
Indeed. The OEIS is just an incredible catalog, thousands upon thousands of sequences. And this one, A000190, it asks a pretty clear question.
Which is?
For any given whole number n, how many solutions does the congruence x to the fourth power, XAO0 mod n, actually have? Counting solutions between 0 and n1.
Right. So our mission today is to sort of unpack that, look at the sequence that pops out and see, why it matters in the OEIS, what it tells us.
And the OEIS entry itself gives us plenty to work with. You've got the sequence terms, formulas, connections.
Exactly. So let's start with the sequence itself. The first few terms go 1, 1, 1, 2, 1, 1, 1, 4, 3, 1, 1, 2, and so on. I won't read them all. There are quite a few listed.
It keeps going, yeah. 1, 1, 1, 8 for n at 16, then 1, 3, 1, 2.
And importantly, this sequence starts at n1. So A1 is A2 is 1, A3 is 1, A4 is 2.
Correct. And what becomes interesting quite quickly is how this count-in behaves as n itself changes. It's not random.
No, definitely not. And one of the really key properties here, something super useful in number theory, is that this function an is multiplicative.
Yes, absolutely crucial. And multiplicative just means if you take two numbers, let's say m and n, and they don't share any common factors besides 1.
They're relatively prime.
Right, relatively prime. Then the value of the function for their product, am times n, is simply am multiplied by an.
Which is super powerful, right? Because it means we can break down the problem.
Exactly. If we understand how an behaves for prime numbers and powers of prime numbers, we can use this multiplicative property to figure it out for any number n, just by looking at its prime factors.
It's like knowing the properties of the basic building blocks lets you understand the whole structure. So speaking of those building blocks, the prime powers, the OEIS gives a really neat formula for A, where P is a prime and E is a positive integer.
It's quite elegant.
The formula is A equals P raised to the power of the floor of 3e divided by 4. So P3e4.
Right. That notation, the floor function here.
Yeah, let's clarify that. It just means you take the greatest whole number that's less than or equal to whatever is inside.
Exactly. So like the floor of 3.7 is 3, floor of 5 is just 5.
And why do we need that floor function here? Seems a bit specific.
Well, think about it. An counts the number of solutions. That has to be a whole number, an integer. But the exponent, 3e4, that might not be a whole number itself.
Ah, right. Like 3 times 1 divided by 4 is 0.75, not an integer.
Exactly. So the floor function ensures we always get an integer exponent for p, which results in an integer value for a, our count of solutions. Guarantees a whole number count.
Okay, that makes sense. Shall we try it out, maybe with P2?
Sure. Let's take P2. If E1, we get 8, 2, 3, 14, you're born. 2, 3, 14. The floor of 0.75 is 0, so 2 agrees in 1.
Okay, A2 is 1. Matches the sequence.
Now E2.
P2 all
A2 is 32.4, 264 year, 2, 1.54. Floor of 1.5 is 1, so 2.
E4 is 2 in the sequence, yeah.
Let's do E3. E2 and 294 euro, 2.25, floor is 2, so 2 of 1 is 4.
A8 is 4. Looks good. One more, E4.
Why not? A2 earns 16, 2 on 2040 yields 2, 3. Floor 3 is 3, so 2 and it's 8.
And A16 is indeed 8. Wow, okay. That formula works perfectly for powers of 2.
It does. We could try P3 as well.
Okay. A3 in, that's E1.
3, 314 nil, 3, 0.75 real, which is the third term.
And A3, which is A9.
That's E2. 3, 3, 3, 4, 4,
Yes.
3, 1.55 yields 3.
And A9 is 3 in the list. Yeah, it's really clean how that captures it.
And now we see the power of putting it together with the multiplicative property.
Right, for composite numbers, how about N6?
Okay, N6. First, prime factorization. 6 must equal A times A3.
2 and 3 are relatively prime.
Correct. So because AN is multiplicative, A6 must equal A2 times A3.
And we just found a 2, 1 and a 3, 1.
So A6, 1, 1, 1, 1.
Which is the 6th term in the sequence. Fantastic. So we don't actually need to count the solutions for excess as 0 mod 6. We can just use the formula for primes and the multiplicative rule.
Precisely. It gives us a much more efficient way to calculate any term AN once we know the prime factorization of n.
That's really elegant. Now, the OEIS page also mentions something called a Dirichlet generating function. It looks intense. Zeta 4's S3 times the product over primes.
Ah, yes. Dirichlet generating functions. They look a bit scary, maybe, if you haven't encountered them much.
A little bit. What's the gist?
Think of it as, well, another way to package up the entire sequence. It's an infinite series, specifically sum a n n s, where s is a complex variable. And the amazing thing is that the form of this function often reveals deep properties of the sequence an.
So it's not just for calculation, it's for understanding structure.
Exactly. The fact that it involves the Riemann-Zeta function, zeta s, and has this product form over primes that immediately tells a number theorist that the function an is multiplicative and is deeply connected to the primes. It allows us to use tools from analysis to study the sequence.
So it's like a coded message about the sequence's nature.
You could say that, yes.
Wow.
A very powerful coded message.
Okay. Moving on to something maybe more immediately practical, the OEIS entry also gives some code snippets. There's one for Mathematica.
Right. The first one listed is often a direct computation from the definition.
Yeah, it says array function n, count array power mod, hashtag 4, n 000190. Looks like it's literally checking every number x from 0 to n1, calculating xo mod n, and counting how many times it gets 0.
That's it. Brute force, essentially. It verifies the definition.
Yeah.
Good for checking small values, but it gets slow pretty fast.
Then there's another mathematical one that seems different. FP,
Really?
P floor 3, E4, A1, A1, 1, and then times at F at factor integrin, araya, 100.
Uh-huh. Now this one uses the method we just discussed. You see the function f, that's calculating our formula, AP.
Right.
So you see the P floor 3, 4.
And then for general n, it uses factor integrin to get the prime factors and their exponents.
Like finding 6 equals 2 to years and 3 years.
Exactly. And then it applies the function f to each prime power factor, like f21 and f31, and multiplies the results together the times at part.
So this code implements the multiplicative property and the prime power formula.
Precisely. Much, much more efficient, especially for large n.
And there's a pair of GP snippet too.
Yeah.
Prod I1, hashtag F15135524. Looks very similar in spirit.
It is. Factor n gets the prime factorization, then it iterates through the factors. Prod I1 takes the prime base phi1, raises it to the power, 3 phi, where phi 2 is the exponent e, and 4 is pri's integer division, effectively doing the floor of 3, 4.
So again, factorization, then apply the formula. It really drives home that this multiplicative approach is the way to go computationally. It's the power of theory informing practice. Find the property, exploit it for an efficient algorithm.
Now, shifting gears slightly, the comments mention something intriguing. This sequence, A00000190, is the shadow transform of fourth powers, which is sequence A000 of 583 shadow transform.
Ah, the shadow transform. It's a specific operation you can perform on sequences. It's a bit technical to define fully here.
Just the gist.
The gist is it's another way sequences can be related. If sequence B is the shadow transform of sequence A, it means the terms of B are sums of terms of A, but selected based on divisibility properties. The OEIS wiki actually has a page explaining it if people are curious.
So knowing the sequence is the shadow transform of the simple sequence of fourth powers.
Yeah.
1, 16, 81, 256 tells us what?
It suggests a deeper connection. It implies our sequence AN, counting solutions, isn't just some isolated thing, but arises naturally from a simpler sequence, the fourth powers, via standard construction. It hints at maybe combinatorial interpretations or other contexts where it might appear.
Interesting. It places it within a broader framework. The entry also links to some articles, Henry Bottomley on Smarandike-type multiplicative sequences,
Suggests exploring other sequences that behave similarly, multiplicatively.
and a couple by Hal Dyson and Hungerbuehler connecting number theory to set theory and combinatorics.
Right. Those titles are fascinating. A number-theoretic conjecture and its implication for set theory, and number-theoretic aspects of a combinatorial function. It really shows how these seemingly specific number theory problems can ripple outwards.
Yeah, you start counting solutions to XAO0 mod n and end up talking about set theory.
It's the interconnectedness of mathematics. It happens more often than you might think.
And finally, there are loads of cross-references to other OEIS sequences, A10445A, A000189, many others.
Following those links is like exploring a web. You see how sequences relate, maybe finding variations like XA0 or XA0, or sequences counting solutions to different kinds of congruences. It helps situate A000190.
And the keywords wrap it up nicely. For non-negative terms.
Yeah. Well, it's a count, so that makes sense.
Mults for multiplicative, which we've seen is key.
Absolutely fundamental here.
And easy, suggesting it's relatively simple to compute.
Which it is, if you use the multiplicative property and the prime power formula. The brute force counting isn't so easy for large n.
Right. Okay, so let's try and summarize this deep dive into A000190. The main point is this sequence counts solutions to XEO0 mod n,
And the crucial insight is that it's multiplicative.
which lets us calculate any term using prime factorization and this elegant formula for prime powers. A equals pre-adjoint.
Exactly. Understanding sequences like this one, they're really foundational for getting a feel for number theory and how the OEIS works. It shows how structure emerges from simple questions.
So maybe a final thought to leave our listeners with.
Well, we focused on the exponent 4 today. What happens if you change it? Consider XEO0 mod n or X00 mod n. How does the number of solutions change? How does that formula for a map adapt?
Does the floor function stay? Does the fraction change?
Those are great questions. The OEIS is the perfect place to start exploring them. Look up sequences for x cubed mod n, for instance. See what patterns emerge. It's a great way to discover more.
Excellent suggestion. Thanks for joining us on this deep dive.
My pleasure.